Hello everyone, welcome to this lecture. In this lecture we will continue our discussion on the candidate cyclic groups for cryptographic purposes, and in this lecture we will introduce specifically the cyclic groups based on elliptic curves. So, let us start with the discussion on elliptic curves based cyclic groups. So, remember in the last lecture we had seen that if p and q are primes where p is of the form r times q plus 1, and if we take all the rth residues modulo p, then the resultant set which we denote as G constitutes a subgroup of Zp star, and we can prove that this set G along with the operation multiplication modulo p constitutes a cyclic group. However, it turns out that for practical security we have to operate or select very large values of this prime p, namely we have to ensure that the p is at least a 2048 bit prime numbers, which actually ends up ensuring that the resultant time of the sender and the receiver is also very slow. So, what we are now going to do is in this lecture we will see cyclic groups based on the points on elliptic curves, and these are basically alternative cyclic groups where the D-log problem, the CDH problem and the DDH problems are indeed believed to be hard. More specifically, if the size of prime that we are going to operate with is of size n bits, then the best known D-log solver that we know for these groups is of order 2 to the power n by 2, and that means it is sufficient to operate with a prime number which is a 256 bit prime number for most practical purposes, and that gives us a highly efficient instantiations of D-log, CDH and DDH based crypto systems compared to instantiations based on prime order subgroups of Zp star, right. So, that is a plus point of these groups compared to the instantiations based on the prime order subgroups of Zp star. Another interesting property of the cyclic groups based on the elliptic curves is that it provides us with additional structures what we call as pairings, which we are not going to discuss in this course because these are advanced concept, but just for your information, this additional structure which we call as pairing can be used to build highly advanced cryptographic primitives such as aggregate signatures, broadcast encryption, functional encryption and so on. So, before going into the exact elliptic curve based cyclic groups that we are going to use for the cryptographic purpose, let us do a warm up and see how exactly elliptic curves over the real numbers look like. So, let big R be the set of real numbers and let A and B be two real numbers or constants publicly known such that this relationship hold, namely 4 times A cube plus 27 times B square is not 0. The reason for this constraint will be clear soon. And imagine we have such an A and B, constant A and B, consider this equation in x and y square equal to x cube plus ax plus b. Then if I plot the points on this equation, or if I plot the x comma y values satisfying this equation, right, and if we take all those x comma y pairs which are real numbers satisfying this equation, and along with that if I take a special point which I denote as O, then the resultant set I call as E. So, for instance, if I take the curve or the equation y square equal to x cube minus x and plot all the real x comma y satisfying this equation, then I obtain this curve. In the same way, if I take the curve y square equal to x cube minus x plus 1 and plot all the real x comma y satisfying this equation, then I obtain this curve. So, what E is basically, once we have fixed the equation, we take all the x comma y real numbers which satisfies this equation, and along with that a special point which we denote as O, and this special point O is called as the point at the infinity, which is kind of an imaginary point which you can imagine sitting at the top of the y axis and lying on every vertical line. So, you can imagine that every vertical line will eventually meet at a horizon at a single point, and that point where all the vertical lines are going to meet is considered as the point at infinity, which we denote by this special notation O. So, that is how I construct the set E. Now, the set of points E that we have defined above is called a non-singular elliptic curve over the set of real numbers, and why it is called non-singular? Because we have ensured the condition 4a cube plus 27b square is not equal to 0, which is a necessary and sufficient condition to ensure that the resultant curve that we have defined here, namely y square equal to x cube plus ax plus b, has 3 distinct roots, because it is an equation of degree 3 in x. However, if we do not ensure this condition, namely 4a cube plus 27b square is not equal to 0, if we let it to be 0, then the corresponding curve or the set of points E that we obtain is called a singular elliptic curve. It will not have 3 distinct roots. So, that is the definition of elliptic curves. Now, what we are going to do here is we are going to define a very sophisticated way of performing operation, the addition operation on the points on this elliptic curve. So, imagine you are given a non-singular elliptic curve over the real numbers, and we define the addition operation on this point such that the way we are going to define the addition operation, it satisfies all our group axioms, namely it will satisfy the closure property, associativity property, it will be ensured we have an identity element and an additive inverse for every point on the curve, and which ensures that this set E along with the plus operation that we are going to define now constitutes an additive group. So, the plus operation is defined as follows. So, we define the point at infinity to be the identity element, that is our definition. So, we define that if we define the plus operation on any point P on the elliptic curve and the point at infinity to give the result as P. So, if you take any point P, which could be the point at infinity itself, and to that point if you add the point at infinity, the result is defined to be the point P itself. So, that is the first property of the addition operation that we have defined here. On the other hand, if you are given 2 points P and Q lying on the curve E, and say the coordinates of the point P are x1 comma y1 and the coordinates of the point Q are x2 comma y2, and neither P nor Q is the point at infinity, then the way we are going to define the plus operation on these 2 points P and Q is as follows. So, we can have 3 of the possible cases depending upon the relationship that holds between the coordinates of P and Q. So, the first case is when x is not equal to x2. In this case, the way we define the result of P plus Q is as follows. So, we define L of x to be the line passing through the points P and Q. So, it is a straight line passing through the P and Q. So, you have the pictorial representation here, and let R be the third distinct point which lies both on the straight line as well as on the elliptic curve, right. So, I am denoting the x and y coordinates of that third point to be x3 comma minus y3, and I call that point to be R. So, pictorially say this curve, this straight line passes through P and Q and it intersects the elliptic curve at the third point, say at R, whose coordinates I denote as x3 and minus y3. So, in this particular example in the pictorial representation, the y coordinate of R is actually positive, but that need not be always the case. So, that is why I am just representing it as minus y3, because if for instance if your Q would have been here, then on passing the straight line or through P and Q it would have met somewhere here, and the y coordinate of R would have been a negative coordinate. So, irrespective of what exactly is the case, it is just a notational issue. The third distinct point at which the line intersects the elliptic curve is denoted as R, whose x coordinate is x3 and the y coordinate is minus y3. Now, what we do here is we just reflect the point R along the x axis, and if we reflect the point R along the x axis, the x coordinate is going to remain the same, but the y coordinate, its sign will get changed. If it was minus y3, it will become plus y3, whereas if it would have been plus, then it becomes minus. And the result of P and Q, the result of the addition of P and Q is defined to be that reflected point. So, that is the way we define the plus operation on points P and Q, where both neither P and Q are infinity point and x1 is not equal to x2. So, now if we want to mathematically compute the exact value of x3 and y3, here is how we can compute. It turns out that x3 and y3 are related to the coordinates x1, x2, y1, y2 by this relationship, and here lambda is basically the slope of the straight line passing through the points P and Q, and the slope of the line passing through the points P and Q comes through this formula, and since we are in the case where x1 is not equal to x2, that means the denominator is not 0 and hence the lambda is well defined. So, that is the way operation p and the operation of addition, now plus operation on points p and q is defined for this case, for the case where x1 is not equal to x2. Now, let us take the second case where x1 is equal to x2, but the y coordinates of p and q are just opposite of each other, right. So, in this case what we do here is the line that we make pass through p and q, it basically ends up converging at the point at infinity, right. So, the idea here is also the same, we actually pass a line passing through the points and p and q and see where exactly it meets the elliptic curve. But in this case, since the x coordinates of p and q are same, but only their y coordinates are different in the signature in the sign, the straight line passing through p and q basically meet the point at infinity, at converge at point at infinity, and that is why we define the p plus q operation in this case to give the result the point at infinity. That means we can interpret 2 points x1 comma y1 and x2 comma minus y1 where x1 and x2 are same to be the additive inverse of each other, right. Whereas, for the third case where x1 is equal to x2 and y1 is equal to y2, we have two sub cases. If y1 is equal to 0, right, then we can interpret y2 to be equal to minus y1, because 0 and plus 0 and minus 0 are same, right. So, if y1 is equal to 0, then we can interpret y2 to be equal to minus y1, and then we basically come to the previous case where x1 is equal to x2 and y1 is minus y2. And in that case, the way we have defined the plus operation, we get that the summation of p with the same point, which is basically 2p, gives you the point at infinity. On the other hand, if y1 is not 0, that means say we have a point like this p and we want to add p to itself, then the line passing through this point is defined in a different way. The line here is basically the tangent to this curve E passing through the point P, and we see where exactly the tangent touches the curve. We call that point as say R, and say the coordinates of R is x3 and minus y3, which is the third point. Two of the points are P and the third point lying on the curve is R, and what we do now do is we just reflect the point R along the x axis, and that is the result of adding P to itself. So, the result P plus P, which is 2P in this case, will be x3 comma y3, and mathematically again x3 and y3 are exactly the same as it was defined for the case where x1 was not equal to x2. The only difference now is that the slope of the line is different here compared to the first case, because in the first case the points P and Q were distinct points, but here the points P and Q are the same points, and that is why the line is the tangent and the slope of the tangent is computed by this formula. And since y1 is not 0, right, we are in the case where y1 is not 0, the denominator 2 times y1 is non-zero, and that is why the slope is well defined. So, that is the way we perform the addition operation for elliptic curves defined over the set of real numbers. But as I said earlier, for cryptographic primitives we want to operate on a set which has a finite size. So, that is why now what we are going to do is we are going to compute or perform operations on elliptic curves modulo a prime number, which will not have nice geometrical representations as we had for elliptic curves over the real number, but property wise we can extend the definition of the plus operation as we have done for the case of real numbers here as well. So, here is how we define elliptic curves modulo a prime. So, let E be a non-singular elliptic curve over the set ZP. Basically what it means is we form a elliptic curve equation here, namely the equation is y square is equal to x cube plus ax plus b modulo p, and we take all x comma y elements or x comma y pairs from the set ZP cross ZP, namely we take all the elements of the form x comma y where x is in the range 0 to p minus 1 and y is also in the range 0 to p minus 1, which satisfies this equation, and along with those x comma y pairs we take the special imaginary point, namely the point at infinity. So, as it was the case for elliptic curves defined over the set of real numbers, the point at infinity serves as the identity element, namely we define that any any point P belonging to the set E. If we perform the plus operation with respect to the point at infinity, then we get back the same point P. Whereas, if we have 2 points P and Q belonging to the set E, which are not the points at infinity, and say the coordinates of P are x1 comma y1 and x2 comma y2, where x1 y1 x2 y2 are all elements of the set ZP, then the plus operation is defined as follows. For the case where x1 is equal to x2 and y1 is equal to minus y2, we define P plus Q to be infinity. This is exactly the case. This is the same as in the case 2 for the elliptic curves over the real number. Whereas, if otherwise if x1 is not equal to x2 or y1 is not equal to y2, then we define P plus Q to be x3 plus y3, where x3 and y3 are elements of ZP, and where x3 will be this value, namely lambda square minus x1 minus x2, of course everything modulo P, and y3 will be lambda times x1 minus x3 minus y1 modulo P, right. And the lambda will be computed in a different way for 2 subcases. If P is equal to Q, then lambda is defined in this way, namely 3x1 square plus a multiplied by 2 1, the multiplicative inverse of the element 2 times y1, and this basically corresponds to this case. That is how we have defined the x3 comma y3 for the real number case. And if P is not equal to Q, then the lambda is basically the slope of the line passing through the points P and Q, which basically is similar to the first case for the elliptic curves over the real number. And it turns out that all these operations that we are now performing here are with respect to multiplication, all the plus operations and all the multiplications operation that we are performing here are modulo P, when we are actually performing operation on the elliptic curves modulo P. And if you see here the way we have defined lambda, this is the element 2 times y1 minus inverse is not 2 upon y1, that is not the case. This should be interpreted as the element 2 times y1 and its multiplicative inverse, which exists because we are performing modulo a prime P operation. And in the same way, for the second case where lambda is of this form, this x2 minus x1 raised to power minus 1 is the multiplicative inverse of the element x2 minus x1 modulo P, which is also guaranteed to exist because x2 minus x1 will be a non-zero value. So, that is the way we naturally extend the definition of the plus operation for elliptic curves defined over modulo a prime. And for an illustration, let us take this example. Say I perform all my operations on Z11, I take my curve to be equation x cube plus x plus 6 modulo 11, and I take my set E to be the set of all x comma y belonging to the set Z11 cross Z11 satisfies this equation along with the point at infinity. So, if you take all x comma y belonging to the set Z11 cross Z11 and see which of them satisfies this equation, then we obtain the set E to consist of these values. All these pairs satisfies this equation modulo 11, and along with that we have a point at infinity. So, since the size of this E is a prime number, namely we have 13 entities in this set E, it follows from a basic fact from the number theory that the set E along with the plus operation that we have defined constitutes an additive cyclic group, and since the order of this group is a prime number, every element in this group except the identity element, which is the point at infinity, can be treated as the taken as the generator for this group. So, for instance, we can take the element 2 comma 7 belonging to the set E, which is a non-identity element, and you can verify that indeed it constitutes a generator, namely different powers of this element 2 comma 7 will give you all the elements of the set E. So, 0 times g, as per the definition, it gives you the identity element, namely the point at infinity, and if we perform the operation 1 times g, 2 times g, 3 times g, then the way we have defined the additive addition operation, we will get back each of the elements from the set E, namely the non-identity elements of the set E once. That means the element 2 comma 7 indeed constitutes a generator of the set E. So, now we have another candidate group, namely the elliptic curve based cyclic groups, and let us see how exactly the D-log problem, CDH problem and DDH problem will look like over these groups, because in the description of the D-log, CDH and DDH problem that we had seen in the last lecture, we assumed that the underlying group operation is the multiplicative operation. But now we just want to recast those definitions in the elliptic curve based cyclic groups. So, what you are given here is the given description of a cyclic group based on the points on elliptic curve modulo a prime, and say the size of the group is a prime number q, and you are given a generator. That means different powers of g, namely up to q minus 1th power of g would have given you all the set E. Then the D-log problem is as follows. The challenger here picks a random index from the set 0 to q minus 1, and it gives g to the power alpha, which basically is alpha times g, which is nothing but the element g added to itself alpha minus 1 times, and the challenge for the adversary is to find out the index alpha. The CDH problem is the challenger has picked two random points from the elliptic curve by picking the indices alpha and beta and computing alpha times g and beta times g, and the goal of the adversary is to compute the Diffie-Hellman function without knowing alpha and beta. And the DDH problem is the challenger prepares a triplet where the first two components are random points from the elliptic curve, and the third component is either the output of the DH function, Diffie-Hellman function with respect to the first two components, or a random point from the curve, and the goal of the adversary is to find out whether he is seeing a Diffie-Hellman triplet or a non-Diffie-Hellman triplet. So, now we have seen the definition of elliptic curves for cryptographic applications. So, the next question that we would like to answer is it the case that all elliptic curves modulo a prime suitable for cryptographic applications? So, before answering that, let us see an interesting result for elliptic curve based on elliptic curve modulo prime. So, let P be a prime and say E be an arbitrary elliptic curve defined over ZP, which could be a singular curve, non-singular curve, namely say E is the collection of all x comma y pairs satisfying this equation along with the point at infinity. Then a very well known bound, which is called as Hashi bound, gives you a lower bound as well as upper bound on the number of points which we have on this elliptic curve. So, this is the lower bound and this is your upper bound. And interestingly, we have polytime algorithms, polynomial in the number of bits that we need to represent a prime P, which can give you the cardinality of the elliptic curve. It can also pick you, we also have polytime algorithms for picking random points from the curve. We also have polytime algorithms for adding 2 points, and we also know how to generate an elliptic curve where the size of the elliptic curve is a prime number. So, the next question that we would like to answer is that is the D-log, CDH and DDH problem computationally difficult to solve in every elliptic curve based cyclic group, and the answer is not really. So, there are certain curves which we should completely avoid for instantiating primitives, cryptographic primitives. So, we cannot take the curves defined over ZP where the size of the curve or the number of points on the curve is exactly P, which because there are well known algorithms for solving the D-log problems in those groups. So, such curves are called as anomalous curve. In the same way, we should avoid curves where the size of the curve is P plus 1, which are called as super singular curves, and we should also avoid curves where the size of the curve is P to the power k minus 1 for a small curve. All these curves are cryptographically weak curves, because as I said earlier, the instances of D-log problem is very easy to solve in this group. That means, if tomorrow you are proposing a new elliptic curve based modulo a prime, then we have to very rigorously analyze the security property of those elliptic curves before we take those elliptic curves and perform operations on those curves to instantiate any cryptographic primitive, say for example, a Diffie-Hellman key exchange protocol. And it turns out that analyzing any newly proposed elliptic curve is a very challenging task. So, an alternative that you can do is that you can trust and use any of the NIST recommended curves, say for example, P256 curve, curve 25519, which have been rigorously analyzed by NIST, and they claim that they have found they have not found any weaknesses in those curves in terms of solving the D-log problem. That means there exist no polytime algorithms to solve the D-log problem for computing the D-log of any randomly given point on those curve, but you should trust the claim of NIST at your own risk. And that is why when a government of any country tries to adopt any cryptographic primitive where the underlying cyclic group is based on elliptic curves, then they become very skeptical of using or trusting the curves which are recommended by NIST, because they believe that there might be some loopholes which only NIST knows, but it is not known in the public domain. And that is why the government for such critical application pushes to come up with new curves and try to analyze those curves and use those curves for instantiating the cryptographic primitives. But it turns out that for many practical purposes these curves are very popularly used for instantiating the elliptic curve and the cyclic groups for instantiating the cryptographic primitives. So, that brings me to the end of this lecture. Just to summarize, in this lecture we have introduced the second class of cyclic groups where we believe the D-log, CDH and DDH problem to be difficult, namely the cyclic groups based on elliptic curves modulo prime. The advantage of these groups compared to the cyclic groups modulo ZP star modulo P is multiplicative modulo P is that here the best known algorithms for solving D-log problem is of order 2 to the power n by 2. So, we do not have to operate with very large modulus, namely 2048 bit modulus, which was the case for cyclic subgroups of ZP star. It suffices to set the modulus size to be 256 bits and we get the same level of security as we could expect from AES 128. And not only that, the cyclic groups based on elliptic curves gives you another additional structure which we call as pairings, which can be used for constructing advanced cryptographic primitives. Thank you.